Okay, in previous topic we learned about how to determine the stability using Roth-Lewis criterion or RH criterion, where we have to create or fill up the table, and then based on the table we check the sign of the sign in the first column, the sign change in the first column. If there is sign change, then the system is unstable. Now we want to see how we could use another method to determine the stability. This method is called a root-locus technique. Yeah. Okay. Our objective of this topic is to plot the closed loop poles, root-locus, for all gain values. Gain values is k. To observe the system response based on the root-locus, as well as determine the parameter such as TR, TS, damping ratio, and so on. Okay, I think this is you should be familiar with this already. So we have input, output. This is standard control block diagrams. K, transfer functions, open loop transfer functions, feedback, right? So now from here, we need to should be able to see what is the roots of the transfer functions of the denominator of the transfer functions as we change or increase the k value from 0 to infinity, right? So we learned that before, right? Because k is become parts of the characteristic equations, hence changing k will change the locations, the value or the roots of the denominator of these systems, right? So this is this is the closed loop systems based on this, right? So from these closed loop systems, we know that 1 plus kg of s, okay, let me draw this. This is our systems, kg of s, 1 plus kg of s, right? So this is our denominator, and then this is our numerator. Okay. Now, 1 plus kg of s equal to 0, that we can find this root, right? So this is, we call it closed loop. This is closed loop. Closed loop. The denominator of the closed loop systems, right? And then we can also sort of, we can say, manipulate these closed loop equations. We can also get this kg of s equal to -1. They are equal, right? So, but if we compare this system and these systems, I could go back to the system that the control block diagrams. This is our systems, right? Okay. Now as you can see here, this one is the denominator of the closed loop systems here. Okay. This is belong to the denominator of that system. Okay. The whole thing. Okay. But then this is open loop systems, right? Okay. So if we can actually find these roots of these denominator of the closed loop systems equal to 0, then we also can find the denominator or the roots of denominator of these open loop systems equal to 1, right? Okay. So instead of dealing with a closed loop CE, right, left, this one, that is often complex. Root locus deal with a simple open loop CE, right? The root obtained from closed loop, okay? This is important. The roots obtained from closed loop CE 1 plus kg of s equal to 0 will also satisfy the open loop kg of s equal to 1. So that means we can use either one. Instead of using this one as a complex, then we can use this one. Okay, the roots obtained from the closed loop one is using Cartesian coordinates, which is x and y, or on the S-plane, real and imaginary, right? But in these open loops, we use the polar, right? Polar form or vector form, where negative 1 contains magnitude and phase component, like this, right? So now this is negative 1, this is vector that represents of kgs equal to -1. So 1 is this one facing this because it's a negative 1. So the angle is 180. So this negative 1 actually represents by this 180. Okay. Okay, now based on this figure, right? So I think it's a bit tricky to understand, but you'll get to it after this. Okay, this is a magnitude of kg of s. So we know that the angle for this one, right, can be the multiplication of 180, right? So it is actually pointing to the same angle, 180, right? 540, and then 900 will be pointing to the same directions. So that means we can actually formulate kg of s equal to this magnitude 1. The angle is 2k plus 1 times 180, where k equal to 0, 1, 2, 3, 4. Okay, so it's always pointing to that directions. Okay. Okay, now we have this how to find this magnitude kg of s equal to 1. So we actually we need to find the length of the vector of the numerator divided by the total length of the pole. Okay. Okay, what does it mean here? We have to once we have the point on the S-plane, we can then draw a vector. That vector will actually represent the magnitude, the total of these the vectors of zeros and poles will represent kg of S magnitude, and then the phase is the total zeros phase minus the total pole phase, right? Okay, what is poles and zero? Okay, I think previously we learned about root denominator and numerator, right? So this is saying that we have systems. This is numerator, denominator. Let's say this is 1, s plus 1. Okay, this is, we call it poles. Pole is the roots of the denominator. Poles, it's just the names. Poles is actually the root of the denominator of the transfer functions. Okay, zeros is the root of the numerator of the transfer function. Okay, so we have poles and zero. Okay, okay, to differentiate between poles and zero on the S-plane, we can use this is imaginary. Okay, pole is represented by x, where 0 represents by O. Okay, this is 0. This is poles. Okay, assuming that our transfer function, this is, let's say, -1, -2. This is getting from our transfer functions as s plus 1, s plus 2. So this is our poles, s minus 1, our 0. This is our s equal to minus 2. This is our poles, right? This is our 0. So then we can plot like this, because 0 minus 1, right? So the symbol is O, and then the poles, the symbol is X. Okay. Okay, now let's consider this example, right? Let's consider this example. We have, this is our transfer functions. When we um, find this TS, we got this K over S plus 2 plus K. Then this is the equivalent in time domain, right? Okay, now changing this K value will change the stability of the systems, right? We increase K. K can increase from 0 in real-time systems, from 0 values to any very high value. We call it infinity. So, so we need to see how the behavior of the poles, right, change as K increases. We can't afford to actually test every single K from 0 to infinity, right? We can't afford, because it's thousand million of numbers. So we need to be able to see the root locus, right, the directions of the roots as K increases. Okay, that's the idea. So we are not going to test one by one, but we need to be able to predict the directions of this K. Okay. Okay, what we're gonna do is we're gonna use this. Okay. First, if we need to prove that with the manual calculations, that what is the behavior of the poles and 0 as we increase K values here. Okay, assuming that we have this is our systems, and then this is our closed loop systems, right? And then this is our open loop system, so K S plus 1 over S plus 2, right? So let's see this. Okay, let me draw this. S plus 1, S plus 2. This is unity feedback systems. Okay, open loop systems, G of S, open loop system, right? Open loop system, transfer function equal to K S plus 1, S plus 2. Our closed loop systems transfer function equal to K S plus 1 over S plus 2, right, plus K S plus 1. Or we can simplify it, K S plus 1, S plus 2 plus K S plus K. Okay. Okay. Okay, now see that. Okay, now as we increase K, let's say just, for the sake of verifying this one, we choose K0 to 10, 100,000. Okay, we just increase randomly. So we need to verify what is the poles. That means the poles of a denominator as this K change, right? As this K change, we need to see how the poles 1 and poles 2, because there are two poles there, change as K increases. You see that as k equal to 0, we have a 0 and -2, which is open loop poles, right? As k equal to 0, so we have 0 here, s equal to 0, s equal to -2, this is 0, 0, right? So the first, these rockers will start at open loop poles, right? Open loop poles, that means we go back to here, that is the where the root locus start. Okay, and then we increase k equal to 1.5, then we calculate this, we got this, and then we can plot this. All right, first one, you see that our open loop is as this one here, this open loop, this is closed loop. All right, as k increases, the first one we need to plot is the open loop poles and open loop 0. Okay, so this is open loop poles is s equal to 0 because this is open loop, k s plus 1 s plus 2. So that means this is our poles, our zeros is s minus 1. Our poles for open loop is s equal to 0, s equal to 2 minus 2. Okay, so we plot this 1 here, which is this one, and then 1 here, which is minus 2, right? So 0 minus, okay, this is our zeros. So there are 3 poles. Okay, there are 3 poles. As we increase k value, we see that the poles is moving from open loop poles towards this, right? So you can see that if I can zoom this, okay, here, right? This is our open loops poles, open loop zeros, open loop poles. As we increase that values, right, this one will start moving to this direction until the infinity, right? This one is getting to -1. That means these poles actually moving towards the 0 when k equal to infinity, and then the other poles actually moving towards this direction. Okay, so now we know that, right? We know that as k increases, this is the locus, the directions of the poles, the closed loop poles, from open loop poles moving towards open loop zeros. So in between the orange color is the directions of the closed loop poles. Okay, so okay, we stop here first.